this video, we're going to learn about indefinite integrals and the net change theorem. We'll start with the definition of an indefinite integral, go over some common integration formulas, and work through lots of examples. Then we'll move on to the net change theorem and learn how integration can be used to find the total change in a quantity over an interval. We'll finish with an example involving particle motion and see how these ideas connect. Be sure to download the free guided notes to follow along, highlight the formulas, and work through the examples with me. Let's begin by learning how an indefinite integral is defined and walk through some formulas that you'll need to know. An indefinite integral is essentially the same as the antiderivative of a function. The indefinite integral is the integral of little f of x dx, and it's equal to capital F of x plus c, where f prime of x is just little f of x. Let's now see how this relates to antiderivatives. The function capital F of x plus c is the indefinite integral of little f of x. Capital F of x is an antiderivative of little f of x. Without the c, it's just one of many antiderivatives of little f of x. And then capital F of x plus c is the same as the indefinite integral of little f of x, and it's the general antiderivative of little f of x. So the general antiderivative of little f of x is the same thing as the indefinite integral of little f of x. Let's now walk through some basic integration formulas that you're going to need to know. We'll begin with some general integral formulas. When you integrate a constant times a function, you can just take that constant out in front and then just integrate the function. If you have the integral of one function plus or minus another function, you can integrate both of those functions separately and then just add or subtract them. These next two formulas are things that you need to make sure not to do. If you have the integral of one function times another function, you can't split that integral up and integrate the two functions separately. Similar to this, if you have one function divided by another function, you can't split this integration up and integrate one function and then divide it by the integral of the other function. The next set of formulas that you need to know, I've categorized into what I call algebraic integral formulas. The integral of a constant k is just k times x plus c. The integral of x raised to a number is just x raised to that number plus 1 divided by the number plus 1 plus c. This formula only works if n is not equal to -1. If n is equal to -1, then you have the integral of 1 over x, and that has a special formula, and it is the natural log of the absolute value of x plus c. The next set of integration formulas are the exponential integral formulas. The integral of e to the x is just e to the x plus c. The integral of b to the x is really similar, except it's b to the x divided by the natural log of b plus c. Now this brings us to trigonometric integral formulas. On the left, we have the integral of sine, secant squared, and secant tangent. And then on the right are the co-functions cosine, cosecant squared, and cosecant x cotangent x. The formulas on each side are really similar, and that should help you memorize these. The last set of formulas that I've included here are inverse trigonometric integral formulas. These are probably the hardest to memorize and might take some practice, and they're the integrals for inverse sine, inverse tangent, and inverse secant. Inverse sine and inverse tangent are usually more common than the inverse secant function. We're now going to walk through lots of integral examples, both definite and indefinite, using common integral formulas. I've included an example of each type that you might encounter. Let's start by going over 3 techniques that you can use for evaluating simple integrals. The first technique is that you can multiply algebraic functions. The second is that you can divide algebraic functions, but you can only do this when the denominator has one term. And then the third one is when you are working with trigonometric functions, and for those, sometimes you need to simplify them with a trigonometric formula. We're going to walk through 4 examples where we are going to evaluate the given indefinite integral, and we'll use these techniques that I just listed. In the first example, we're actually not going to use any of these techniques because I thought it would be good to just start off with a basic one that doesn't involve any extra simplification. For this one, we just have to remember what the formula is. When we integrate a constant, we have to multiply by x, so that's 4x. And then the next one is 2x. We're going to add 1 to the exponent, so 2 plus 1 is 3. And then you divide by that exponent. And then our next one is 5 times the integral of e to the x, and that's just e to the x. And then we can't forget to add on plus c. And there's our answer. In our second example, we are integrating x times the quantity 1 plus 2x to the fourth. This is an example where we have one function multiplied by another function. When we go to integrate this, we want to start by multiplying these 2 functions out. This gives us the integral of x plus 2x to the fifth. We're just multiplying the x through. Now we can go ahead and do the integration. The integral of x is x squared divided by 2, and then we have a 2 times the integral of x to the fifth, and that's x to the 6 over 6 plus c. Now we just have to simplify this. This is x squared over 2 plus x to the 6 over 3 plus c. Now let's look at our third example. For this one, we are integrating 3x minus 2, all divided by the square root of x. Notice that we have one term in the denominator, and that means that we can divide each term in the numerator by this term. I'm going to start by rewriting the square root of x as x to the 1/2. That'll just make things easier. Now we can go ahead and divide each term in the numerator by x to the 1/2. So this gives us 3x over x to the 1/2 minus 2 over x to the 1/2. And we're going to simplify this before we integrate it. 3x divided by x to the 1/2 is just 3x to the 1/2. And then we subtract 2, and I'm going to rewrite this last one as x to the minus 1/2. That way we can use our formula x to the n. Now we can go ahead and integrate. This is 3x. We're going to add 1 to the exponent. 1/2 plus 1 is 3/2. And then we divide by 3/2. And then we have minus 2x minus 1/2 plus 1 is 1/2. And we divide by 1/2. And then we have our plus c. Now let's go ahead and let's simplify this. In our first term, our 3's are going to cancel. And we just have a 1/2 in the denominator, so we can bring that up and write it as 2x to the 3/2. And then we'll bring the other 1/2 up and multiply by 2. So 2 times 2 is 4. So we have minus 4x to the 1/2 plus c. And there's our answer. The last indefinite integral that we're going to do involves a sine function. We need to simplify this integral before we can actually integrate it. And to do that, we are going to have to use a trig formula that relates sine 2x to to sine x. And that formula is sine 2x is equal to 2 sine x cosine x. That's a really good one to memorize because it comes up a lot. Now we can rewrite our integral as 2 sine x cosine x, all divided by sine x times dx. We can then see that our sine x's are going to cancel, and this gives us the integral of 2 cosine x dx. And we can just go ahead and integrate that. We'll bring out the 2, and then the integral of cosine is sine. There's no negative there. And then we tack on our plus c. And that's the answer. Let's now look at some indefinite integral examples. We're going to now walk through 5 indefinite integral examples. Remember that an indefinite integral is equal to a number and not a function. Our first example is the integral from 0 to 2 of the quantity 2x plus 5 times the quantity 3x minus 1. Since our integral is one function times another function, we want to start by multiplying out those functions. So this is the integral from 0 to 2. We can use the FOIL method to multiply this out. Let's multiply the first terms, so that gives us 6x squared. And then we'll multiply the outer terms, which is minus 2x. And then the inner terms, which is 15x. And then the last terms, which gives us minus 5. Since we have two terms with an x, we want to combine those before we integrate. So we have 6x squared plus 13x minus 5. Now we can go ahead and integrate. Our first term is x cubed over 3. And then we have plus 13. And then we have an x squared over 2. And then minus 5x. And this is being evaluated from 0 to 2. This is equal to 6 divided by 3, which is 2. And then we're going to have 2 cubed. You substitute in the upper limit first, plus 13 times 2 squared divided by 2, minus 5 times 2. And then we subtract off the lower limit, but the lower limit is 0, so we can just subtract 0. Now let's see what this gives us. 2 cubed is 8, so 2 times 8 is 16. And then we have in our next term right here, 4 divided by 2, so that's just 2. So 13 times 2 is 26. And then we subtract 10. So this is just 16 plus 16, which gives us a value of 32. Now let's look at our second example. In this example, we are integrating x divided by 3 minus 3 divided by x. We wouldn't have to, but I'm going to go ahead and rewrite this just to make it a little bit easier. I'm going to write our first term as 1/3 x, and then our second term as minus 3 times 1 over x. That just makes it easier to see that we are integrating x and then 1 over x. This gives us 1/3 times the integral of x, which is x squared over 2, minus 3 times the integral of 1 over x, which is natural log absolute x. And we're going to evaluate this from 1 to 3. We're first going to substitute in the upper limit of integration. And we'll combine the 3 and the 2, so we have a 1/6, and then we have 3 squared, minus 3 times natural log of absolute 3, which is just 3, minus our two functions evaluated at x is equal to 1. So this is 1/6 times 1 squared, minus 3 natural log 1. I always like to write it like this so that I can remember to multiply that negative through to both terms. Now let's see what we get. Our first term is 9 over 6, and then we have minus 3 natural log 3, and then our next term is minus 1 over 6, and then natural log of 1 is equal to 0, so we don't have to worry about that term. 9 over 6 minus 1 over 6 is 8 over 6, minus 3 natural log 3, and then let's divide 8 and 6 both by 2, so that gives us 4 over 3 minus 3 natural log 3. And that's our final answer. I've included this next one because I think this one can be difficult. We are integrating 1 plus cosine squared theta divided by cosine squared theta. Whenever I see something like this, I always think, oh, maybe I can use the formula sine squared theta plus cosine squared theta is equal to 1. But then I see that in the numerator, we have 1 plus cosine squared theta, not 1 minus cosine squared theta. So using that formula is not going to help. Then I look at it again and I say, oh, we just have one term in our denominator. So what we can do is we can rewrite what we're integrating and divide each term in the top by cosine squared. Let's see what this gives us. This is the integral from 0 to pi over 4 of 1 divided by cosine squared theta plus cosine squared theta, all divided by cosine squared theta d theta. Now let's simplify this. 1 divided by cosine squared theta is secant squared theta. And then cosine squared divided by cosine squared is 1. And now we can integrate each of these terms separately. The integral of secant squared is tangent theta. You can always think when you're doing this type of problem, what function do I take the derivative of to get secant squared? And that function is tangent. And then the integral of 1 is just theta. And we're evaluating between 0 and pi over 4. This gives us tangent pi over 4 plus pi over 4 minus tangent of 0 minus 0. Tangent of 0 is equal to 0 because it's sine over cosine and sine of 0 is 0. Tangent of pi over 4 is equal to 1, and then we add pi over 4. So our final answer is 1 plus pi over 4. Let's look at our fourth example. We are integrating 1 divided by the square root of 1 minus x squared. This is an integral where you can only evaluate it by knowing the formula. This integral is equal to the inverse sine of x, and we're going to evaluate that from 0 to 1/2. This gives us the inverse sine of 1/2 minus inverse sine of 0. You want to remember that an inverse trigonometric function is just an angle. So the inverse sine of 1/2 is an angle whose sine is equal to 1/2. So if you think about the unit circle, the angle whose sine is equal to 1/2 is pi over 6. So we have pi over 6 minus the angle whose sine is equal to 0, and that is going to be 0. So we subtract off 0, and we get an answer of pi over 6. Now let's look at example 5. We are integrating the absolute value of sine x. What we have to do for this problem is we have to break up the integral into where sine is positive and where sine is negative. Over here on the right, I have drawn the unit circle, and we have to think about sine. Sine is going to be positive in this quadrant, and then negative in quadrant 3 and quadrant 4. We are integrating from 0 to 3 pi over 2. So let's mark this 0, pi over 2, pi and 3 pi over 2. We can now break up our integral into the first piece where sign is positive, and that is going to be from 0 to pi. And we have plus sine x dx. And then we have the piece where sign is negative, and that is from pi to 3 pi over 2. And we're going to integrate minus sine x dx. Now we just have to integrate. The integral of sine is minus cosine. So we have minus cosine x from 0 to pi. And then we have a minus the integral of sine, which is minus cosine. So we have to be really careful here with our negatives. And that goes from pi to 3 pi over 2. This gives us minus cosine of pi minus cosine of 0. And then we have plus cosine 3 pi over 2 minus cosine at pi. Cosine of pi is -1, so we have minus -1. And then we have plus cosine of 0, which is 1. And then we have plus cosine 3 pi over 2, which is 0. And then we have minus cosine of pi, which is -1. So this gives us 1 plus 1 plus 1 for an answer of 3. Let's now learn all about the net change theorem and walk through an example. The net change theorem says that the total change in a quantity over an interval can be found by integrating its rate of change over that same interval. The net change theorem tells us that the integral from a to b of f prime of x dx, where capital F of x is the quantity that is changing and f prime of x is the rate of change of that quantity, this integral is equal to f of b minus f of a, where f of b minus f of a is what we're looking for, and it's the total change in f of x. So basically, we are just integrating a rate of change to get total change. Let's walk through an example so that we can see how this works. We are told that an oil storage tank initially holds 4,000 gallons of oil. The oil is leaking out at a rate of 100 plus 4t² gallons per hour. We want to find out how much oil is in the tank after 3 hours. Our tank has some oil in it. Oil is leaking out, and we want to find how much is left in the tank after 3 hours. Let's start by assigning some variables to what we need to find and what we're given. We need to find the amount of oil remaining after 3 hours. So let's assign capital A of T, A being for amount, is the amount of oil remaining after 3 hours. It's always a good practice to write down what your variables are. We need to assign another variable to the amount that is leaking out because we're given a rate of change of what is leaking out. Let's let capital L of T be the amount of oil leaked out after 3 hours. And then let's also put down that we know what this rate of change of L is. So we can say L prime of T is the rate of change of oil leaking out, and that is 100 plus 4t². Now let's think about this 4,000 gallons. Our tank initially holds 4,000 gallons, So the amount remaining after 3 hours, which is A of t, is going to be the amount that we start with, 4,000, minus the amount that leaks out, and that's L of t. So all we have to do now is find L of t. To do that, we are going to use the net change theorem, and it tells us that capital L of t is the integral from 0 to 3, because we have 3 hours that we're looking at, of L prime of t dt. Now we can just substitute in what L prime is. It is 100 plus 4t squared dt. Now we can integrate that. This is 100t plus 4t cubed divided by 3. And we're going to evaluate this from 0 to 3. This gives us 100 times 3 plus 4 times 3 cubed divided by 3 minus 0. So this is 300. It looks like we can cancel in this next term one of our 3's out. So we had 3 cubed. We can make that 3 squared and divide by 3. So we just have 4 times 3 squared. That's 4 times 9, which is 36. So we're going to add 36. And this gives us 336 gallons. Now we can find what A of t is equal to. Our A of t, that's the amount left, is going to be 4,000 minus 336. And this gives us 3,664 gallons. And that's the amount of oil that is left in the tank after 3 hours. We're now going to walk through a particle motion example where we're given an acceleration and need to use integration to find velocity and distance traveled. We are told that the acceleration function in meters per second squared and the initial velocity are given for a particle moving along the line. Here is our acceleration. It's equal to 2t plus 3, and we're told that the initial velocity, v of 0, is equal to minus 4. We want to find the velocity at time t and the distance traveled during the given time interval, and our interval is where t is between 0 and 3. Just to make things easier, over here on the right, I've written down the formulas that relate position, velocity, and acceleration. When you're given position, you can find velocity and acceleration by differentiation. And then when you're given acceleration, you can find velocity and distance by integration. And that's what we're going to do in this problem. We want to start with part A, finding the velocity at time t. So let's just write down, we're going to find v of t. V of t is the integral of our acceleration function, a of t. Let's now plug in what that is. We are integrating 2t plus 3 dt. This gives us t squared plus 3t, and then we can't forget to add on our arbitrary constant. We can find what this arbitrary constant is by using our initial condition, v of 0 is equal to minus 4. So let's let t be equal to 0. So we have v of 0 is 0 plus c, and that's minus 4. So we know that c is equal to minus 4. That tells us then that v of t is equal to t squared plus 3t minus 4. Now let's look at part B. We want to find the distance traveled during the given time interval. Our distance traveled is typically noted by s, so the distance traveled is going to be s at 3 minus s at 0. That's just the distance at the end of the time interval minus the distance at the beginning of the time interval. The fundamental theorem of calculus tells us that s at 3 minus s at 0 is the integral from 0 to 3 of s prime of t dt. I'm going to put a little star here because I think that's the hardest part of the problem. Once you know that, everything else is not as hard. The next thing we have to do is we have to realize that the derivative of position is our velocity. So s prime of t is v of t. And now we can just substitute in the v that we found in part A. So we're going to integrate from 0 to 3 of t squared plus 3t minus 4 dt. Let's see what this gives us. This is t cubed divided by 3 plus 3t squared divided by 2 minus 4t. And we're evaluating this from 0 to 3. This gives us 3 cubed divided by 3 plus 3 times 3 squared divided by 2 minus 4 times 3. And then it's always nice when our lower limit is 0 because we just subtract off 0. 3 cubed divided by 3 is 27 over 3, which is just 9. And then we have 3 times 3 squared is 27 divided by 2 minus 12. This gives us minus 3 plus 27 divided by 2. We'll get a common denominator of 2, and that's minus 6 plus 27. So this gives us an answer of 21 divided by 2, and we need to put units with that. If we go back up to the top, we were told that our acceleration is meters per second squared. So that means that our distance is in terms of meters. So our distance traveled is 21 divided by 2 meters. And that's it. You've learned the definition and formulas for indefinite integrals, practice applying them to different examples, and seen how the net change theorem connects integration to total change. To really master these problems, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.